Gnanam paramam dheyam. Knowledge is supreme.
We have seen in a previous class that two-level systems cannot give you laser. The laser is light amplification by stimulated emission of radiation. So the idea is, when light goes in to some medium and then when light comes out, number of photons going in, well, number of photons coming out should be more than number of photons going in. That can only happen when there is a net stimulated emission. If you think of steady state, of course, there is absorption, stimulated emission, spontaneous emission, everything going on. But what is the net effect? Is there a loss of photons or is there a gain in number of photons? That is what we are trying to discuss here. Okay? If there is a gain in photons, then only you can think of making a laser out of the system. So that happens only when there is population inversion. This is something that we worked out in the previous class by a very simple kinetic approach. Okay? Population inversion is an essential requirement for this net gain to happen. And as we have seen, is that you cannot get population inversion if you have a two-level system. So you cannot make a laser out of a two-level system. There was a paper in Science, I think 3 years ago or 4 years ago, where they claimed that they have obtained lasing from a two-level system, but then they talked about something very bizarre. They talked about negative absolute temperature, and the impression I got from reading that paper is that it is not a true two-level system. All right. So until something very drastically different happens, two-level system does not give you a laser. What about three-level system? What about four-level system? Is it possible to generate a population inversion if you have, say, a three-level system? Now, in fact, three-level systems also can be of two kinds. Let us say I have this level 1. Now, instead of going into detail of singlet, triplet and all that, I will just write level 1, level 2, level 3, level 4. What they are depends on the system. Let us say this is level 2. You cannot have population inversion between them. Suppose there is a metastable level between these two. Then what happens? Okay, a very simple example that perhaps most of us will understand is that think of an organic molecule. For organic molecules with all paired electrons, the ground state is a singlet, right? Then this state is also a singlet excited state, and in between you have a triplet state. Do we all know this? This energy order: singlet, excited singlet, triplet. So as you know, if this is a singlet state, this is a triplet state, then transitions between singlet and triplet are not allowed. We are going to deal with it in more detail when we talk about electronic spectroscopy. For now, if you don't know this, let us take it axiomatically. So what happens is, and suppose these are electronic levels. What is the meaning of electronic levels? When you start the experiment, all the population is here, right? The energy gap is too much. So you start with this, excite the molecule to state 2, and then by some non-radiative process, if this is singlet, this is triplet, then what is that non-radiative process called? ISC. And what is ISC other than Indian school certificate? Inter-system crossing, right? So here we mean inter-system crossing. So this takes it here. Now see, to start with, before this, so this process is actually called pumping. Populate the excited state is actually called pumping. At time 0, when pumping begins, is there any population in the excited state? No. So question of population inversion doesn't arise. Now see, initially let us say there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 multiplied by 10 to the power. What is Avogadro number? 10 to the power? Yeah. So 10 multiplied by 10 to the power 23 number of molecules. Okay, each is 10 to the power 23. Suppose you start pumping and you manage to send 2 of these here. Have we achieved population inversion? No. But then you know that this transition between 3 and 1 is not allowed. See, that is an essential condition. Okay? In a system like this transition has to be disallowed. If that is the case, then what will happen? This lifetime of state 3 is going to be long. It is going to be long enough for you to have a chance of keeping on populating it until you have population inversion. Do you understand what we are saying? Let us say it has a lifetime of several milliseconds. Can triplet states have lifetimes of milliseconds? Can triplet states have lifetimes of seconds, minutes, hours? Triplet states can actually have lifetimes of hours. Okay, right. So you have something like this, long enough. So if this lifetime of state number 3 is long enough, then what you can do is you can keep increasing the population of it gradually by pumping continually until you achieve population inversion. Right? You understand what I am saying? Rate of pumping has to be fast, lifetime of state 3 has to be long. In that case, the moment, now if we reach this situation, we have 6 in state 3, we have 4 in state 1. Now population inversion is achieved, right? Now you can have stimulated emission, strong stimulated emission, which takes all these 6 into 10 to the power 10 molecules down to the ground state all of a sudden. All right? So what we see is that for a 3-level system, I'll call this 3-level system of type A, we can have lasing. But have you noticed what kind of lasing it is? Does this laser remain remain on all the time? No, right? Initially, until population inversion is achieved, there is no lasing. Okay? So what kind of a laser is it called? It's called a pulsed laser. So if you look at the output, for the time that is required, so this is time, for the time that is required to build population inversion, there is no intensity. The moment population inversion is achieved, you get a huge burst of light. Then again, there is nothing. Then again, when the population inversion is achieved, you get a huge burst of light, and so on and so forth. A good example of this class of lasers is ruby laser that gives you the so-called giant pulses. Okay? So first thing that we learn is that you can have lasers that are pulsed. And we also learned that for 3-level systems like this, you can make lasers. Now let us think of 3-level systems of type B. And this is the system that is discussed in your Macquarie and Simons book. With a little bit of modification, let us say this is level 1, level 2, level 3. Now let us say that this transition is allowed. But this transition is not allowed. Okay? Now what will happen? We'll start with the same situation, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 into 10 to the power whatever is there. Okay? Populate level 2. Let us say I have sent even one of these here. Do I have population inversion between level 2 and level 1? No. But what is the population of level 3? 0. So do I have population inversion between level 2 and level 3? We do. So what will happen is that the moment even one molecule goes there, you already have population inversion between level 2 and level 3. Okay, and level 3 population is never built up because let us say that there is a non-radiative, efficient non-radiative relaxation happening between level 3 and level 1. Okay, so this efficient non-radiative relaxation keeps on depleting the population of level 3. The moment level 3 gets populated, it gets depopulated non-radiatively. In this situation, what you have is, you have, let us draw a laser like this. You can have lasing between level 2 and level 3. Alright? Now, let me ask you something. In this case, if I try to draw a similar output, if I want to draw the similar graph of laser output versus time, what kind of plot should I get? Here I got pulsed operation. Will I get pulsed operation in case B as well? Yeah? No, right? Because the moment you pump, the moment even one molecule is here, you already have population inversion between level 2 and level 3. So you are going to have, let's say this y-axis is intensity or output or whatever you want to call it. This is going to be hopefully constant. So now for this one I have pulsed operation, pulsed laser. For this kind of a 3-level system, I have what is called a continuous wave, in laser terminology it is very common to call it CW laser. Okay? And of course what you could do is, for these systems, what is the rate of excitation? Rate of excitation is B12 rho nu 12 into population of level 1. What is the rate of depopulation of this? This is KNR multiplied by population of level 2. What is the rate of depopulation of this? If you consider only stimulated emission, it would be B31 rho 31 nu N3. The point to note is that rho 12 and rho 31 are not going to be the same. Okay? Yes. And also you might have A. Well, you are going to have A always. If B21 is there, then A21 also has to be there, as we know. So you have to consider that as well. Alright? What he's saying is this B21 is going to be very small. We are saying the transition is not allowed. In that case, why do we have lasing at all? See, when I say not allowed, I don't mean it's exactly 0. It is small. But the issue is that can be overcome if N3 is sufficiently high. Rate constant is small, but if you can have a large enough population, then you can still get it. Okay? Then the rates can become equal. So similarly, you can write those terms here and you can work out the equation. Next, let us add one more level. Say 1, 2, 3, 4. In this case, what we are saying is that there is an efficient non-radiative channel between 4 and 1. There is an efficient non-radiative channel between 2 and 3. Understood? Now what will happen? Take the system to level 2. The efficient non-radiative channel takes it to level 3. Now we are saying this is allowed. So what is and the moment anything comes to level 4, it gets depopulated once again by your efficient non-radiative pathway between 4 and 1. So population of 4 is practically maintained at 0 all the time. So what will happen now? Even if one molecule comes here, you have population inversion between 3 and 4. So this is where your laser might be possible. Okay? This is a 4-level system. A very common example of 4-level system is the so-called Nd:YAG laser, neobidium, yttrium, aluminum, garnet. Yttrium, aluminum, garnet is just the matrix. What matters is ion. It has levels like this, and it gives you laser. Now, what will be the output? Is it going to be continuous wave or is it going to be pulse? 4-level laser? It's going to be CW, right? This is also something that gives you a CW laser. Alright, so these are the different kinds of lasers. Quickly, okay, what are we discussing now? We are discussing say laser basics. Now, so very quickly let me just tell you what is there inside a laser. First of all, you have what is called a gain medium. Gain medium means your molecule or ion, whatever it is, that actually gives you the stimulated emission. Okay, it can be solid, it can be liquid, it can be gas. Very common example of gas laser is CO2 laser. Well, nitrogen laser is also there, but I am not taking its name for some reason. Very common example of solid state laser is what I just told you. Well, two examples that we have discussed. One is ruby laser, the other is Nd:YAG, iridium, yttrium, aluminum garnet laser. And then in liquid phase, many times what you want to do is you want to take a dye, an adhesive dye, dissolve it in some solvent and use that as the medium that is going to give you the light. But dye lasers are becoming less and less and less popular. One reason why dye lasers have been popular traditionally is that they are actually tunable. They can give you many different colors at your will. But they have problems as well. The dye lasers dissolved, well, dye molecule dissolved in organic solvent, you can understand. It's smelly, your container can leak, dyes are carcinogenic, your hand gets, it's happened many times to me while doing experiments. Your hand gets stained for like days, so they're not very nice things to work with. So they are by and large being replaced in most of applications by solid state lasers. So you have this gain medium. Next, what you need is you need a pump. Okay, pump means something that is going to populate the excited state. So you can do it either by using electricity or by using a light source. Right? You can have some other light source or you can have an electrical source also. So you have some pumping source. Okay? And then when light comes out, what you do is you want to catch the stimulated emission in a particular direction, and then you want to, if you want to amplify, suppose one photon goes in and two photons come out. That is not too much of amplification, right? If you can make those two photons come back and go through the gain medium once again, then you will get 4 photons. Is that right? Make those 4 photons come back and go through the gain medium once again, then you get how many? 8 photons. So the number of photons can in principle get doubled in every, it can get 4 times in every round trip, right? So the way we do it is you put one mirror here and you put one mirror here. They are always curved mirrors because what you want is you also want to focus your light at the center of the gain medium, that is that gives you best results. Okay, but just for the sake of simplicity I will draw one line. Okay, so this is what happens. Let us say you get one photon coming out of here, it goes, hits this mirror, comes back. That gives rise to 2 photons. These 2 photons hit this mirror, come back, gives rise to 4 photons. When they come back, they give rise to 8 photons and so on and so forth. This is how you get a very quick build up of light intensity of number of photons, whatever is you are more comfortable with. Okay, so this is called the gain medium, and this entire thing containing this pump, gain medium and these 2 mirrors is called the laser cavity. Now length of cavity has an important role to play here, because you understand we are saying photons, but we cannot neglect that wave nature of light also, right? And as you understand, you have this wave going back and forth. Essentially what you want to do is you want to build a standing wave, right? What is the condition of having a standing wave? Yeah? Yes, so what is the condition for that? So let us say the cavity length is L. That should be equal to lambda multiplied by something. N by 2, right? You should have integral multiple of half wavelengths. Is that right? So this is the condition that has to be fulfilled. So what light you are dealing with actually determines what kind of cavity length you should have. Okay, it's a different matter what actually this n is. Generally this n is not 1 or 2, n is a large number, but we don't have to go into so much of detail in this course. So this is your laser cavity. All right. Now, what I have shown you here is that suppose these two mirrors are perfectly reflecting mirrors. Then you are going to have build up of energy within the cavity, right? But then it's a closed loop. You understand what I'm saying? We have the gain medium, we have these two mirrors. Let us say these two mirrors are perfectly reflecting. Then it is true that number of photons will keep increasing within the cavity. How do I get it out? I have to get it out, right? There are two ways of doing it. The simplest way of doing it is to use a highly reflecting mirror on one end and what is called an output coupler in the other end. Output coupler is commonly referred to as OC. The only difference is that here reflectance is 100%. Here reflectance is, let us say, 95 or 97%. 97% reflectance. That means what? 3% of light will go out. Right? This gives you a way of getting the light out also. This is the simplest way of doing it. There are more complex ways of doing it. Somebody mentioned in electric field. That is right. So there are things like things called Pockels cells that you can use here, and you can switch the light out without having to use an optical, having to use an output coupler. But let us not get into that much of detail now. If you understand this, we are good enough. Are we clear so far? Any questions? If not, this is the end of the first module.